Hi everyone, this is a tutorial on getting started with AnyLogistix. We will cover certain aspect of network optimization, how to do the network optimization, and then we will touch upon a bit on how to do greenfield analysis. So quickly starting with a network optimization exercise. So this is the welcome screen, and then you can close it and then be on the network optimization tab. And then you can click on file and go to a new scenario. So in new scenario, you can name the scenario as per your wish. You can select the time window for which we want to run the optimization and then click on OK. Left-hand side, this part of the window, you see that we have all the scenarios listed. And then on the middle part, you see that there are certain choices for each of these scenarios. So one is data, where you can see the tables that you can configure. And then the details about the experiment. How do you want to experiment? What is the period for which you want to experiment? And those details, which we will cover later. And then we have on the right hand side the GIS map, which you can actually drag to the site that we want to, and then we can actually zoom in and out of those particular regions. On the left hand bottom corner, we have the tables which are categorized into basic, all, and new news. So by the little details that we have created the scenario, the few tables got filled in by itself by AnyLogistix, which are categorized under the in use because these tables are filled. However, there is a set of basic set of tables which ALX suggests that it should be populated. And then the rest of the tables are categorized under all, where we find all the tables that are used in network optimization. And we want to create a customer. So this is a customer. We clicked on this on a single click, and then we can navigate to the place where we want to actually create a customer. So we maybe zoom in and out and then double click to create a customer. So what it did is that it created a customer and filled it in with the details. You can actually name a customer as customer maybe one. The type is customer, and then the location got updated as in the locations table, which we can find in the location in the in-use tab. So in the locations table, this got updated with a particular latitude and longitude. What we can do is that we can either drag and drop this customer to our desired location, or if there is any particular city or city name or place name that we want to use instead of this pre-filled latitude and longitude, that we also can do. So probably say we want to place this customer in Stuttgart, Germany. So what we do is we put the city and country name, and then we do the autofill coordinates. But just to keep your eye on this latitude longitude, because as soon as I switch it on, then it will change. So as we see that the latitude and longitude has changed because ALX in turn had populated the coordinates based on the provided city and country name. Now we will create another entity called warehouse or distribution center, and we place it at a particular location by double clicking on the map. And we can see that in the DCs and factories table, one entry got inserted as a of type DC. And similarly, we can change the location or specify a particular location and using ALX's autofill coordinates feature. And then we can And we can create a factory in any location. And we will see that the DCs and factories table got updated with a factory, and the locations we again can give a in any location. Suppose it is in Paris in France, and then we can do the out-of-field coordinates. And finally, the supplier. So we can include a supplier supplying to these entities and create a supplier likewise. And we can leave it as is if we don't want to specify the particular coordinates in a particular city. To run the network optimization experiment, what we will do is that we will click on here, and then the period of start and end date got automatically selected, and we will use USD as a unit, and then we can click on run. So what we see over here is that there is a negative profit and there is no flow. That then in the supply chain, in the between the entities that we have created, there is no flow of products to product flows. And we select a vehicle type. So by default, ALX has created a vehicle type. So we will select for the time being the default vehicle. Still, we see that there is no profit. There is no sales of any of the products, and the flow amount is zero within the supply chain. In the product storage table, we will keep some initial stock of any product or the products that are in use, so that there is some flow of products from any location. So here we see that there is a flow that has happened in the network. Now, if we go to the product flows table in the output, we see that site 2, which essentially is the factory, there is a flow from there to the customer of the amount that we have got in the initial storage. So change the name of the sites to a understandable name so that we can identify them by the names. So now we want the flow to happen from the factories to the DCs and from DCs to the customers. So what we can do is in the product storages, instead of having all sites in the facility, we can select a first DC and we say that there is no initial stock in the DC, and then we add a factory. And we say that the factory has some initial stocks. So that from the factory to the DCs, and then we will add another row which will specify that from DC to the customer. And then we will also define the product flow as from factory to the DCs, and then another row to say that it will flow from DC to the customers. And we will specify the vehicle type, and we will check the rest of the things. In the paths table, we may want to specify a type of product flow. Maybe the cost of flow between the DC and the customer would be lower. We'll just specify a particular value and then we run the experiment again. So there it says that there is a vehicle type which is not defined or specified from the DCs to the customers in the paths table. So again, we select the vehicle type and then click on the experiment. So now we see that it should give us a flow where the flow is happening from a factory and it is going to a DC first and then from DC to customer. Let's see. So yeah, as expected, we see that the factory to DC, the amount, and then from DC to customer. That's the flow that's happening. Now we will try to understand the demand table. And we saw that there is a flow of 730 items. And why is that so? We will be able to understand that we saw that in the product storages table, there is 10,000 units. But we see that the flow is happening 730. Why it is 730? To understand that, we must see how the demand is defined in the demands table. So if we go to the demand, the customer one, the demand is at an interval of every 5 days of quantity 10. So what happened is that um, um, in a total year, if we consider it as 365, so we divide it by 5. So every 5 days there is a demand um, of 10 units. So, so what we see is that there are 73 buckets if we have the demand every 5 days multiplied by the quantity. So we see that this is the quantity that is the total demand for the entire year, and that's what it is. We see that it is flowing between the entities. We can see how the connections have established because we have defined the paths and the product flow by clicking on this filter phone shape and then clicking on the show connections. Here this shows that how um, the connections are happening. And how we see that why there is a curved line between the factory and the DC, but a straight line between the DC and the customer is because when we define the path in the factory to DC, we have a curved is allowed, straight is not toggled in. But here we see that from between DC and customer, the toggle for straight is there. It means that it is giving us the straight path. Now, if we toggle it off, then it will also give us the actual road path. Now, now we will try to understand the total cost of transportation and how it is calculated. So we have defined the the transportation policy as product and distance based. So what is happening actually is that the flow is 730 cubic meter and multiplied by the distance of 466.143. 730 multiplied by this, and then we have the and then the transportation cost for the DC to factory to DC is 0.05. So 0.05 multiplied by 730 multiplied by the distance. So this is 17014.224, which we exactly see the transportation cost over here. Similarly, if we see what is the total volume and the distance, so distance is this. So the total volume again is 730 cubic meter multiplied by this distance multiplied by, I think we have to define the cost for each the unit cost as 0.01. So then the total cost we see is 3686.67, which if we see for this particular length is what it is. So this is how the total cost is calculated for a particular transportation policy, which we see over here is product and distance based. We will find the product policy that we have defined is here under the cost calculation. That is the transportation policy, and then the parameters are as it is defined in this way. Now we will try to understand what is the demand fulfillment table in the output. So in the output, we see that there is a demand fulfillment table. And we see that there is a one customer there, the demand was 730 and then satisfied is 730. So 100% satisfied. And then by default, the selling price was set to be 1. So the total revenue was 730. Another important table to understand would be the objective members. So objective members is where we are defining the objective of the total optimization. So here it is the profit maximization, where we are trying to maximize the revenue with minimizing the total costs. So costs include the carrying cost, the inventory carrying, the transportation cost, the production cost, etc. Now we can try to understand how to fill in the data, not through the UI, but through the Excel, because if there is a lot of data, we would like it would be easier to fill the or build the model through an Excel template. So what we will do is right click on the scenario that we have created in the first place, and then export the scenario to Excel file, and then we can export it. And then we can go to the open the Excel. We'll try to understand the Excel file. So this is the customer tab where all the customers will be listed. So the name of the customer we had was customer 1, and then the customer 1 locations. So all the location master will be here with the country name, the city name, and then the latitude, longitude information. The DCs and factory similarly will be in the DCs and factories tab with the DC names and their type of whether it is a DC or factory, and the location master attribute. The demand would be in the demand tab. The demand, the ID columns are gets created by ALX itself. However, we have the customer for whom the product is the demand is, and then the order interval is 5 days of 10 quantities as we saw in the UI. And then we can specify the if there is any up and down penalties. Here that we see this demand as a periodic demand, but if we want that, okay, our model will only be getting the demand at a single point of time, then this would be we would want to change it the demand type as historic demand. So what we will do is we go to the demand table and then change the demand type to a historic demand, and then probably we can add a quantity of 10. So what it says is that this model gets for this customer, the demand for this product is of total quantity for the entire period for which we are running the model. So we can see how it is, and we can actually name the column. We can name the file differently than what is there initially. And we can open the Excel again, and we can check what is the file name. So now if we see here, there are two demand tabs. One is the demand, and then there is a historic demand. So in the historic demand, we have the demand ID, which is connected to the main demand by that ID. And then we have the actual quantity. So this is that this is how it is defined for an historic demand, where we are specifying that the demand has only come once for the entire period. So far what we have seen is that there is a flow from the factories to the DCs and DCs to the customers, where the flow is happening because this product is available already as initial stock in the factories. However, now we would like the factory to actually do some production instead of having some initial stocks. So what we would do is that we don't need the factory to be in the product storages. Rather, we would want a production to be added. So we don't have any production data yet, so we can search from here. and we can add the production as a new row in the table. We can select the particular product. We don't have a we can say 1 USD is the production cost. We now run the experiment and we will see that there is some still some flow from the factory, and we will see how much it has manufactured. So we see that there is a flow from the factories to the DCs and DCs to the customers, and then we will see how the production has happened. So in the factory, since the demand was 10, so the manufactured amount was 10. Now what we will do is we will see how to add a custom constraint in the terms of production constraint, so that we have two products, SKU1 and SKU2. And we will say that the same machine can make two SKUs. And then the maximum capacity for the machine is 100 unit, say, and it cannot make more than 100 for any of the SKUs. So we created two SKUs, SKU1, SKU2, and then we will say that the total demand for one of the SKUs is 100, and the other SKU would be 110. Right, and then we would define a custom constraint where we will say that the total volume cannot exceed the capacity of the machine. So what we say is that this factory, we can rename it as a machine, you know. So what we will do is essentially we will create a, or let's say the factory has a this factory is a machine which makes two SKUs. SKU1 and SKU2, and that's it. And then we will label this, put a factory SKU1, maybe. Similarly, we can name it factory SKU2, and we will go to custom constraints table. What we will do over here is that we will say that we will add an expression here saying that factory SKU1 and then factory SKU2. Okay, so it should be less than equals to 200. We'll see choose a custom continuous variable or integer variable, and we can say that limit inputs. Yeah, it will be continuous variable, where we say that okay, it should not make below 200. 200. It should exactly make 200. So now with this custom constraints, we run this experiment. So what we see over here in this result is that the product flow has happened from factory to DC and DC to customer of 100 unit only for each SKU, because the maximum throughput of the machine was 200. But the demand was, if we see the demand data, that demand was for 210. But since the capacity, or we said that the capacity of the machine is not more than 200, it cannot manufacture. So whatever it manufactures, whether it will manufacture only SKU1 or SKU2 or both, the total amount should not exceed the 200. So yeah, and then if we see the demand table, so we saw that the demand was 210, but actually it has produced only the quantity of 200, as we see in the output. So that's why for each SKU, even the SKU2, the demand was 110, it has only produced 100 because the total capacity of the factory was 200. We can confirm that in the production flows table as well, where we see that the product produced quantity is 100 for each of the SKUs. We can specify the production throughput in the production table itself. We say that my maximum throughput for the machine is 200, and so it cannot exceed 200 as the capacity. So here also we can actually give the throughput of the specify the maximum throughput of the factory. Now, now we will try to understand how to insert the maximum throughput and the custom constraint through an Excel. So again, as we have done earlier, we can export this scenario to in an Excel template. And we can look at the data. So what we see over here is that in addition to whatever we discussed earlier, we can see what is the production table looks like. So the production table here we have the site where the production is happening, the products, and then the maximum throughput as we have defined, and then the label that we have given for each of these production lines. This label is important because we want to put a custom constraint on the total amount to be manufactured. So to understand the custom constraints, we can go to the we have to see the linear expression variables and the linear expressions tab. So in here, so we have put the linear expressions as the labels that we have defined in the production table, as we saw just now. And then we say that these two values added because the linear expression 0 is representing both these rows in the production table. So linear expression essentially what it says is that the lower bound and upper bound for that particular linear expression is 200. So suppose there is another machine, right, and we want this to be that machine is also manufacturing, say, suppose 3 products, and we want to bound the amount of, I mean, the machine throughput to a particular value. So let's see how we can do this. So, so suppose we say that we will add another factory in the decision factory table. We'll say it's a machine factory 1. We will set its type as a factory, and then we'll go to the locations tab and then put the factories as a Radomsko, which is a city in Poland. Then we will set the auto field coordinates so that it automatically set its coordinates to the particular location where we see that this particular factory that we created as a factory 1 got created in Poland. Now we will create 2 more products, which is product 1 and 2. In addition to product 1 and 2, SKU 1 and 2, we will say SKU 3 and 4. And we will add these two as a production capacity. We will see that the factory 1, the new factory that we have added, are producing SKU 3 and SKU 4, and maybe we will add another product to make it clear. Maybe SKU 5 as well. And in production, we will add this SKU 5 as well here. And then we will say that we can select all of them and together, and we can specify the production cost as we want. And then maximum throughput, we can say that the maximum throughput is 300 machines. And then similarly, similar to what we did, we will label it as factory 1 SKU 3, factory 1 SKU 4, and factory 1 SKU 5. And what we will do is that we will say that the demand we will go, and we will say that the customer 1 has a demand of SKU 3, has a demand of SKU 4, and SKU 5. Customer, and we will select all of them and together click a space bar, and then we can specify all of them as required. So we are specifying them as a 100, 100, and 200. So 100, and then this one is 200. Okay, so the demand for these 3 SKUs together is 400. These are 3 SKUs as we have specified are being manufactured in the factory 1, which has the maximum throughput of 300. So demand is in total with for these 3 SKUs is 400. However, this factory has a maximum throughput of 300, so it cannot manufacture more than 300. So that custom constraints we will add again, as we saw earlier in the earlier example. So what we will do is, here we will add expressions where we will say that factory 1 SKU 3, factory 1 SKU 4, and factory 1 SKU 5. And then we will say that it's less than equals to, and then we will put a continuous variable where we will say that the maximum throughput, it cannot exceed 300 unit. Okay. So this ensures that we will we have specified the maximum production throughput for this factory. Again, we will have a look at what we did just now before running the experiment. So what we did essentially is that we added 3 new SKUs. We added a factory, and then we specified that factory's location to Poland. In the production table, what we did is we said that, okay, these 3 new SKUs are being manufactured in this factory, and we have labeled them. Also, we have said that the factory's total maximum throughput is 300. And in custom constraints, we said that the optimizer should return a production allocation to limit the output, so that it's whatever combination of this SKU 1, 3, 4, and 5 it is suggesting to manufacture should be less than or equal to 300. So even if the demand is 400, it should be less than or equals to 300. We'll go to the paths table and then add a path from factory 1 to the DC location, as well as in go to product flow and add a flow from the factory 1 to the to the DCs of vehicle type. We will specify the vehicle type. So here we see that the factory to DC, as we have seen earlier, SKU1 and SKU2, and then we'll be able to see that the factory 1 is sending the SKU3 and SKU5. As this is a suggestion from the optimizer to saying that it is more profitable to send SKU3 and 5 in quantities of 100 and 200 instead of sending SKU3, 4, and 5 each of 100 units. This is because it doesn't matter it is more profitable to send less SKUs to the from the factories to DCs, because it will maybe this is causing less transportation cost. However, if we set the cost of factory to DC, the cost selling price of factory SKU4 more than SKU5, so probably the optimizer will suggest to manufacture SKU4 also. So we'll see that. So what we will do here is that we'll go to data and then the products table, and we see that the selling price is same for all of them. So it doesn't matter for the optimizer to decide whether it should manufacture 3 or sell 3 and 5, or it sells 100 units of each. Now, suppose I may increase the selling price of this product to 2. And now let's run the experiment and see what it suggests. We got a result, and we see that it is suggesting to send SKU 4 now and 200 unit of SKU 5. So we will now see if it is not suggesting SKU 3 because the cost of SKU 5 and 3 are same. So now see if we increase the cost selling price of SKU 3, how does it suggest? So we'll go to the products table, and in SKU 3 we also specify the selling price to more than SKU 5 is, right, and we'll run this experiment. So now what we see is instead now it's actually, as we were expecting, it is actually suggesting to send 100 units of each of SKU 3, 4, and 5. So it's even if the demand of SKU 5 was 200, but since the max capacity is 300 for this factory, it is suggesting to manufacture 300 units only. And since the selling price of SKU 3 and 4 are more than SKU 5, so it's also suggesting to manufacture 100 units of SKU 3 and 4, and also 100 units of SKU 5 because that is the demand there is a demand for SKU 5 from the customer as well. There is something called soft constraint and hard constraint. So now what we need to understand that is this, since we have increased the selling price of 3 and 4, so that's why it is suggesting. However, if we suppose say that I need to satisfy the entire 200 quantity of SKU 5, even if the selling price is less, then there is a way to enforce that constraint as well. So what we do is that we go to demand, and in demand we see that we have defined the down penalty as some value, which essentially makes that particular demand as a soft constraint. So what we can do is here is that we can put it as a 0. So what it means is that it can not miss this demand. So if it can miss these demands while optimizing, but it should not miss this demand. So now what will happen? Let's see if it's so what the expectation would be is that the optimizer will suggest to send the entire 200 quantity, manufacture the entire 200 quantity in the factory for the SKU 5. And so let's see that. So as expected, we see that here, since we have made it a hard constraint, so it is actually forcing it to send the entire 200 quantity of SKU 5. And then since SKU 3 and 4 had the same selling price, so it didn't matter which one it should choose. So actually it chose any one of them randomly because they had the selling price same. Now if I make the selling price of SKU 4 more, then we should see that it is suggesting to manufacture the SKU 4. So we'll do so. So here we will go and then we'll increase the selling price to 3, which is essentially more than the selling price of SKU 3. And we'll go to the experiment and run it. So here, as expected, we are seeing that it is suggesting to make a flow or manufacture SKU 4 in factory 1 because the selling price of SKU 4 was more. And again, anyway, SKU 5 it has to because it's a hard constraint. Now we will understand how to specify these constraints through the Excel template. So what we will do, as earlier we have done, is that we will export this particular experiment into an Excel and see the template. So first we will go to the production table and see how it looks. So all these site locations, the product informations, the throughput information, and then the labels are defined over here. And then we will see the how the linear expression and linear expression variable tabs looks like. So as I was mentioning earlier, that in the previous example, we only had one factory and two SKUs, so linear expression 0. And then the next factory that we added was factory 1, and we had SKU 3, 4, and 5, 3 products. So we have the linear expression 1. And the linear expression variables is that it shows that the first linear expression 0 should be the bound is 200. So that is the maximum capacity of throughput of the machines, and then the second one is the 300. So all these three, including the manufacturer should be manufacturing quantity should be within 300 volume units. Now, so far we have used only one unit of volume, which is meter cube, and we can actually work with different volume units. So what we can do is like find a unit table and add a unit. We can say that the unit is cargo unit, and we can define the product unit in pieces. So what we can do is that pieces is a unit which is by default comes with AnyLogistix. However, its cargo unit is something which is custom defined. So we have to um, define the conversion factors from pieces to cargo units. So what we will do is that we have a unit conversions table. Here we can add the products for which the pieces, how many pieces of SKU1 amounts to. So suppose I say that 10 pieces of SKU1 amounts to 1 piece of cargo unit. 10 pieces of SKU2 amounts to 20 pieces of SKU2 to cargo units. Likewise, we can add all the rows for all the SKUs. Okay. And then we will see that if all the tables has the same units or not. So we go with the tables as one by one. Here in the demand table, we see that there is no place for defining the volume unit, and essentially what happens is that it will assume the units as the products are defined in. And then we have paths. In the paths, we are defining the 1 centimeter cube. So actually, we have to convert it into the unit that we want to calculate the cost in. Similarly, in product flows also, we have to define the product. Okay, so it is actually defining in the product unit. So what happens is that whatever the units the product table is defined in, so it will take that thing. However, so similarly, we would might want to, change that into the product unit as well. So what I'm saying is that a cargo 10 cargo unit is the volume of a vehicle. So depending on how much the demand is, it will still be able to in one vehicle we should be able to carry 10 cargo units. So if the total demand and the total flow from one entity to another becomes more than 10 cargo units, then it will send two shifts of this same vehicle. Now in the experiment, when since we are calculating it in pieces, so either we can or CU, so we can either calculate the statistics in pieces or in CUs. And we see that the volume is being calculated in the pieces as it is defined in the products table. Now we will see how to define the changes in the units table and unit conversions in the Excel template. So we will export it. And we will go to the units table first. And we see that we have defined the unit. So any new unit that is custom defined, we can add it here. And likewise, we have to define the unit conversions as we have defined. So what we have to do is essentially we have to write the product, the from amount and the to amount and the to unit. This ID table is being generated by AnyLogistix itself, so we don't have to bother about it. One more thing that would be useful to understand would be the min load ratio in the paths table. So this column actually what it specifies is that any transportation which is below a certain threshold would be considered in an LTL shipment which is less than truck load, whereas any transportation above that volume would be considered as an FTL shipment. So what that means is, suppose I have a particular lane where from DC to customer, I'm saying that there is a lane and then I would want another shipment to be added in the same lane, where I would say that it is again a fixed delivery, for example, or maybe it's a distance with just distance with fixed cost, where I say that, okay, for the variable cost at each fixed cost is 100. So what that means is that any or maybe for 10, for example. So what that means is that for an FTL volume, FTL shipment, the fixed cost, no matter how long you are shipping it, is 10 USD, and then for each additional each kilometer travel, it is 0.02 cents. So that's how this fixed cost and distance is declared. And what we are saying is that we will consider the shipment as an FTL, where we are saying that if the load is more less than greater than 50% of the entire volume, then it will be considering this shipment, because ideally all FTL shipments are cheaper than FTL shipments. So if the volume is more than what is of 50% of the entire truck load, then it will be considered as a FTL shipment. So what this means is that when we have defined the cargo unit as 2, and we are saying that capacity as 2 cargo units. So means that if there is a volume of shipment of 2 cargo units, then it is a full truck. So that means that when we define in the past the min load ratio from DC to customer is 0.5, means that if there is any volume which is more than or equal to 1 cargo unit, then it will use this transportation lane. And essentially what happens is that all the LTL shipments are actually costlier than an FTL shipment. So we will try to see if any volume which is becoming more than one cargo unit. And then if the volume is more than one cargo unit, then we should see that there is a shipment in the FTL mode between the DC and customer. So essentially, any FTL shipment we should see in the vehicle flows tab in the output. So what we see that there is one flow which is like from the DC to customer has happened in the vehicle, and then that has become the vehicle capacity was 2, and the total volume was to be shipped was and we will be able to see what, and then we don't see over here whether it's a vehicle FTL or LTL. We only will understand by the by the cost it has taken. So because the same vehicle we are using for both FTL and LTL, so you would understand. Though we would understand that there is a LTL shipment of from DC to customer, but we don't know which shipment it has happened. So what we will do essentially is that we will create another vehicle type and keep that vehicle type especially for the FTL shipment. So what we will say is that it is a vehicle type of LTL, and then this is a vehicle type of FTL. Right. And then will capacity increase to 50 for both of them. So LTL capacity doesn't matter, so we will anyway keep it 0, and we will say that the FTL is 50 cargo units. So what we have to do is that we have to specify that particular vehicle type in that. So since we are defining the FTL shipment in the FTL mode, we also have to specify the vehicle type FTL and LTL in DC to customer. Now it will happen. So here we can see that it has specified that which vehicle type it is choosing to ship from the DC to customer. What is the cost associated? How many CUs it has shipped. So we see that the total cargo units being shipped as 32 cargo units. So what we could have done is that we could have increased the total volume of the shipment truck of the FTL to maybe 50 cargo units, because it is sending 32 cargo units and we have the main load ratio as 25 cargo units. So 32 cargo units is anyway more than 35 cargo units. So we will see again a full truckload of one or two shipments. So now we see that there is a one trip only because the volume of the truck is more than the total products being shipped. So the total volume of the truck is 50 cargo units, and the total product unit is 33 cargo units. So it is able to cater to the volume, the required volume. So since we are able to define the paths as well with the mean load ratio, and then we have defined different vehicle types in the paths table, we can export the scenario and we can name it like this. We can open this and we can go to the paths table to see how it is looking. So what happened essentially is that we have defined two types of transportation. One is with the product and volume distance, and one is the volume, the distance with a fixed cost. So how this is like, this is the columns are a bit different. So both the transportation policies are being declared within the same template paths, but it has different value under the columns. So this is something which we need to take care while we are defining different transportation policies in the same template. Okay, now we will turn our attention to how to do a greenfield analysis. Okay, so this is how a greenfield analysis experiment looks like, where we have the customers and then the demand. The customers will be basically these are the two information that we would need to fill in for a GFA experiment. And what we do is that we go to the GFA experiment and we specify how many sites we actually are looking to open, and then run the experiment, and it will give us the potential sites that it suggests based on the center of gravity methodology. So what it does is that it senses the demand and the location of the current location of the customers, and based on that, it shows where the new DCs should be located. So if we see there are 5 DCs that it has suggested, and it shows which DC can serve which customer of which product and how much quantity, what is the distance to be covered, and it shows also the new site locations in a summary of their location as well as the latitude and longitude. And we can actually see the network that it suggests. So which DC being served, which customer is being served from which DCs. And this is showing the straight line distances. However, we can actually do a GFA with roads experiment, which it actually will specify the it will consider the road distances instead of considering them as a straight distance. So here also it suggested which are the new site locations that it is looking at, and it can show which locations it is suggesting to be served from which DCs. And it also shows the product flow. So what essentially happens is that actually this is a probable flow that the probable site locations that this is suggesting based on the customer's locations and their demand. But it might happen that slightly there might be one location which is might be suggested in the sea, or maybe in some mountainous location where actually setting up a DC is impossible. So in that case, what we can do is actually we can specify the particular location around that region, suggested region where we can actually open a DC. We'll see that in a minute, but before moving to that, what we essentially want to see is that, as we mentioned that in the GFA experiment, we already have decided that we want 5 sites. But maybe based on the service distance, we want the optimizer to suggest how many sites it should open. That none of the DCs to the customer's location should be more than 500 kilometers. So here we are not specifying the number of DCs, but asking the tool to suggest how many DCs essentially should be opened. So here in this, by this, it is asking again to actually open 5 DCs based on the service distance, which is same as the one that we have specified. But we see that one of the DCs being specified seems to be slightly on a offbeat location where it should not be suggested. So what we can do is actually we can convert this into a network optimization scenario. And then in the optimization scenario, we can actually specify where should the DCs be located exactly. So we need not use the exact location that the that the tool has suggested, the greenfield analysis has suggested, but actually we can play with this particular DC, so we can actually based on an understanding of where it should be located, we can place them by zooming more into that particular area. And then if we consider that it should be beside a highway, then we can drag that particular DC to beside the highway and then accordingly run the network optimization experiment to see that whether opening the new DCs in those locations actually has reduced that overall transportation cost. So thank you for staying with me, and hope this tutorial is useful for you to conduct network optimization as well as greenfield analysis experiments. Thank you.